So let's start the second talk of mini-series of Sergey Alexandrov from the University of Montpellier about modularity of Calabi-Yau threefolds. Sergey, please.
Yeah, thanks. So I recall you that 2 days ago, what we have done, we just studied various definitions of mock model forms, mock model forms, the generalizations like high depth mock model forms, Jacobi forms, and you will see that all these, you will see today that all these objects, they actually appear in our story. But before that, we still need to learn something about the so-called indefinite theta series, which will also play a very important role in our story. And actually, in this theta series, they can be seen as maybe one of the most canonical examples of all that modular objects which we had before. So let me introduce this theta series. So let's consider some d-dimensional lattice equipped with some bilinear form. We will also have a dual lattice defined like this. And we will also need the so-called residue class, which is element of this factor lattice. By the way, this factor lattice has the dimension equal to the determinant of the quadratic form evaluated on the basis elements of the lattice. So this is the dimension of this guy. There will be also the so-called characteristic vector, but in the first approximation, you can just forget about it. It's needed to deal with odd lattices, with odd quadratic form. If it's quadratic form is even, you can forget about it. And then if we define theta series like this, so that's the standard definition.
Sergey, sorry about interrupting. You see in mathematics, kind of your bilinear form is integer, of course, yeah?
Yes, yeah.
All right, which you didn't say. Now, when you say x such that x dot y belongs to z, x belongs to what a priori?
Well, that's the point, that x can be rational also.
And so x belongs to a Q-rational vector space generated by the lattice lambda. Yeah, just for mathematicians.
Okay.
Yeah, because it's not clear absolutely from what is okay. All right, and characteristic vector. It's what? It again? It belongs to lambda.
Yes, and if you see if t squared is even, then you can put it to 0. But if it's odd, then roughly speaking, you can take p equal to 1, something like that, some basis element of the lattice.
All right, so you fix mu. So I'm a bit confused. No.
Mu is kind of rational, therefore it's non-trivial shift.
Yeah, okay. Everything will okay, good.
So and here I assume, so this formula assumes that my quadratic form is positive definite, and then this formula is well defined, so it's convergent, and the claim, so that's the standard fact, that this function is a vector valued Jacobi form of weight given by half of the dimension of the lattice. And you remember Jacobi forms, they're also characterized by an index. So the index in this case, it's a multivariable vector valued Jacobi form. So multivariable because you see the elliptic variable z is a vector here. So in that case, the index is a matrix. So I denote this matrix. What happened? Something pop out on my screen. Okay, so that's so the index is given by a matrix which represents the quadratic form. So I didn't introduce notation for it. It's well, it's just this. Well, I denoted by a point here.
So I'm confused. Weight is d divided by 2, and what's L
Yes.
over 2? It is what?
Well, it's okay. Let's denote the quadratic form by Qij. Then the index is a matrix Mij given by half Qij. Okay. So the quadratic form with k squared is equal Qij ki kj. Okay.
Okay, and Q, I forgot the notation for Q. It's 2 pi I tau, yeah?
Q, yes. Q is exponential 2 pi I tau.
Yeah, okay.
So that's the standard fact. But now let's imagine that our quadratic form is not positive definite, that it has some minuses in the signature. What happens? Well, then just this formula is not well defined, because for tau in the upper half plane, it's this sum is just not convergent. So the first problem, which we have, just how to make it convergent. To understand how what to do, let's consider the case of the simplest non-trivial case of Lorentzian signature. Lorentzian signature, which means that the signature of my quadratic form is d minus 1, comma 1. Okay? So then what to do? The claim is then that you can make the theta series to be convergent. Well, of course, well, there are plenty ways to make it convergent. You can introduce some damping exponential factor and so on, but the problem is that you want to keep your theta series holomorphic. And if you want to keep your series holomorphic, there is essentially only one way to make it convergent, is to insert a combination of sign functions. So the idea is that you insert certain kernel here, phi of k, and in the case of Lorentzian signature, this phi of k is very simple. It's just the difference of two sign functions, minus sine v2 dot k, where v1 and v2 are certain vectors. And the claim is that if all these vectors, as well as their scalar product, they're all negative, then such formula is well defined. It defines a convergent theta series. So it's easy to check. Okay, but now we come to another problem. Before we had a theta series which was a modular form, namely Jacobi form. So nice modular transformations. Of course, once you introduce this difference of sign functions, they will spoil modularity. But suppose I'm interested in modularity. I want to have a modular theta series. So how is it possible to upgrade the theta series which I just defined to something modular? Or properly speaking, it means finding a modular completion of this theta series. And the claim is that there is a very simple trick how to do it. So it was understood by Zwegers, and the trick is very simple. Just take any sign functions which we had before, like v sine of v dot k, and just replace it in the kernel above by the error function with the following argument: 2 pi tau 2 minus v squared here, so it's just the norm of the vector, and v dot, and let's write here k minus beta, where beta is a component of z. Namely, I took my elliptic parameter z, and I decompose them like alpha minus tau beta, where alpha and beta, they are real vectors. So the claim
what are the notation? What is erf? What is
erf is the error function.
What is error function? We are algebraic geometers, symplectic topologists. What is error function? We don't have to read a table of integrals and know all special functions. It's kind of, it does not ring the bell.
If I remember correctly, it's integral of Gaussian exponential.
Integral of Gaussian exponential from what? From minus infinity to the argument in the brackets of what?
From zero. I don't remember the concrete normalization, so there will be some factors of pi somewhere, but it's roughly speaking something like that. Up to.
All right, but then if you replace signum by something very strange, that something very strange should give you a signum at some limit.
Yes,
and there
exactly.
are too many.
Yes, exactly. So in the limit where for example, the argument of error function goes to infinity, you get you need to normalize it properly, by some square root of pi probably here. I don't remember the precise normalization, but okay. So you get the sign function in the limit x goes to infinity.
Also, I'm confused with this v square. If it's v square, and the
it's
argument,
just the norm.
But your form is not positively defined. What if v square equal
you remember
to
my
0?
vector, I took it with negative norm.
So okay. Of course, I don't remember. Maybe. Okay. All right.
Okay. So then, and in fact, you see the new thing. What happens here is that there is tau2 sitting, which means that once I define my theta completion of my theta series with this new kernel, it will not be holomorphic anymore because there is dependence on imaginary part of tau. And this is a typical situation of mock modular forms, which we saw before. So what happens actually here is that the original holomorphic theta series is a mock modular form, a more precise mixed mock modular form, as I introduced in the previous time. And what I constructed just now is its completion, which is a modular but not holomorphic. An original mock modular form had the modular anomaly but was holomorphic. So that's typical situation. You trade one feature for another. So what happened? Sorry, I somehow I closed the file. Just 1 second. I'll have to share the screen again. Where is it? Here. So okay, so this is how it works for Lorentzian signature. But what about generic signature? So suppose our signature is d minus n, comma n. So what happens in this situation? Again, we have two issues. The first issue is convergence. So how to ensure convergence? Again, the claim is that you need to insert certain kernel constructed from sign functions, and the simplest possibility to ensure convergence is to insert product of differences of signs. So you write something like that to I dot k, where the vectors v1i and v2i should satisfy certain conditions, which I will not specify, but there is a set of conditions which ensure that if you insert this kernel, you get a convergent theta series. That's one problem. it's easy to solve. But what about the second problem? And how to construct completion of such guy? In fact, what happens is that in this case, the theta series is an example of the high depth. It's a high depth mock modular form or mock Jacobi. And the depth is precisely, so the depth is equal to n. And so we come to the problem of how to construct completion, so how to construct something modular. And again, there is a very simple recipe. So how to do it? Just expand this product of differences of signs. So you get sum of monomials, and each monomial is a product of certain sign functions, right? Like this, from 1 to n. So the claim is that this recipe tells you is that you just need to replace each such monomial by the so-called, well, I'll write, then I'll tell the name, to tau 2, k minus beta, where beta is again essentially the imaginary part of the elliptic parameter. So, and this is called the so-called boosted generalized error function. So what are these guys? Well, as follows from the name, they're just generalizations of the error function. Well, here I prepared the slide where I introduced this object. To be fair, I mean, it's not. It's not important, the concrete form of these functions. So let me just go very, very quickly through these definitions. So you see, first we defined the so-called object En, which is just the normal generalized error function. So this is generalized error function. Generalized error function. And you see, it's just a convolution with the Gaussian kernel of this product of signs. And it depends on a certain matrix. So M is a n by n matrix. And U is some n-dimensional vector. And you can see that for n equal 1, you just get the standard error function, and the similar properties we had before. If the argument goes to infinity, you get you return back the product of sign functions. And there are actually many kind of rotational symmetries, so that actually the function does not depend on all components of the matrix. For example, for n equal 2, we have matrix 2 by 2, so it has 4 parameters, but actually the function depends only on 1 parameter. In the case n equal 3, instead of 9 components of the matrix, the function depends only on 3 parameters. So you see, there is a lot of symmetries. Okay, and then once you have these functions, you define the so-called boosted generalized error functions just by properly specifying the matrix and the argument, of this the original error function. You need to choose here certain basis, but in the end it turns out that function doesn't depend on the basis. Well, but you see, essentially it's just again convolution of the product of signs with the Gaussian kernel. And you need to go to these boosted functions because here you see I defined function with the argument given by n-dimensional vector, but I want a function which plays the role of a kernel of my theta series. And to have a kernel, I need that it depends on my lattice vector. And lattice vector is a d-dimensional vector. And n is less than d, typically, so I need to embed somehow my this object into kind of larger space. And this is done by using these definitions. And again, there are many properties which they have, but the most important one, which will play a very important role in the following, is that if one of my vectors is null, namely its square is 0, then somehow the function is factorized. So this vector decouples from the rest, and the function reduces its rank. So what this means in practice, it means that if one of your vectors in the product of science functions is null, you roughly speaking, you don't need to complete the corresponding function by the corresponding error function. So this vector is kind of modular. This sign function is modular by itself. It doesn't require completion. So that's kind of the moral of the story. Okay, so this is what everything what I wanted to tell you about this indefinite theta series. And next, I want to. Sorry, I forgot one important remark also. That actually the. Okay, so here I'm talking about null vector, but the question: can I take null vector or not? Because you remember here, for example, the Lorentzian case, I wrote that my vector should have a negative norm. In fact, you can see from this formula why it reduces to the error function reduces to the sign function, because the norm becomes 0, so the argument goes to infinity, and as I wrote, the error function reduces to the sign when the argument goes to infinity. But the point is that this might spoil the convergence. So if my vector is null, I need two additional conditions to make everything convergent. So first of all, I need that my vector v, which is null, so let's say v0, it belongs to the lattice, my lattice lambda. Or maybe some its rescaling belongs to the lattice, so let's say alpha, where alpha is some number. So what it means essentially is that its coefficient in the basis of the lattice must be rational numbers, roughly speaking. Then it works. But also, not really. It works only if you have this beta parameter here. So if you put beta, for example, to 0, so you remove your elliptic parameters, then the theta series become divergent. So you really need beta to be non-zero. And that's very, this will be very important. Okay. So let's continue. And now I would like to continue with some basic facts about Donaldson-Thomas invariants, more precisely generalized Donaldson-Thomas invariants, because this will be the main topic of the following talk. So what are generalized Donaldson-Thomas invariants? T invariants. Actually, I will not be able to give a proper mathematical definition, which, as I understand, is quite complicated. But roughly speaking, what these guys do, so there are certain invariants, which I will call omega of gamma. So they count certain semi-stable cogherent sheaves on Calabi-Yau threefold. Semi-stable cogherent sheaves.
Your Calabi-Yau will be compact or not?
Mostly I will be interested in the compact case, but sometimes also non-compact on Calabi-Yau. Okay, so these cogherent sheaves, they are characterized by Chern vector. Yeah, so there is certain Chern. But I will use physics notation. So instead of the Chern vector, I will use the so-called electromagnetic charge vector. And this guy will have components P0, PA, QA, Q0, where roughly speaking, this corresponds to Chern 0, this is Chern 1, and so on. There is a very simple linear relation between components of these Chern classes in a basis of even cohomology and these charge vectors. But what is important is that my p's, which I call magnetic vectors, they're integers, whereas q's will be rational numbers. So there will be some rational shifts in there.
Listen, Sergey, maybe it will fly in the physics audience, but mathematicians, at least I have questions. So this map from which assigned to the Chern class element gamma, gamma is an element of what?
Okay,
Because
I
there are
can.
possibilities. It can be
Okay,
image of the Chern class under under the isomorphism of I even don't know. Is it an element of a cohomology group with what? With rational coefficients or with integer coefficients? Because with integer there are questions.
let me write the formula, and I hope it will be clear. So the map, precise map, is given by this dot of tau x, where x is my Calabi-Yau. So if I introduce basis of even cohomology, right? 1 omega a omega a.
Yeah, but with rational coefficients, sorry.
Yeah, so here qa and q0 are rationals. But how they can be rationals? Well, you can see from here. So what you do, so they're rational because there is the square root essentially of the third class, right?
I don't know.
You expand in the
Chern class a priori, I mean, I don't know. I mean, from
no
my
Chern classes are
student
integers.
time, no, Chern class is not an integer,
Uh,
it's an
uh,
element. It depends, of
sorry.
course, of your definition. Maybe somehow you normalize it, but there is an isomorphism between K-theory and rational cohomology, yeah? And so then the class of E, which belongs to the K-theory, goes in general to the collection of Chern classes. Am I mistaken? No. And so these are rational things, and in the definition of Chern class, you have denominator. So then
Okay,
it's a
but
bit,
yeah,
it's
but
a
what?
bit. So maybe you can somehow, there is a normalization which I forgot. It's, yeah, which
Yeah, but it's fine because again, for me, what is important is just that p's are integers, q's are rational, and
I understand that it's important for you, but for me it's important to be free of contradiction. And so I don't care what kind of. I remember actually from some physics, whatever, that gamma should be an element, the charge, they speak about charge lattice. So
yes,
gamma
yes.
should be an element of the free abelian group. So no, okay. And all right. So then I do not understand what you are talking about. Rational, no, it's free abelian group. It's isomorphic to Z in some power.
Yes, it is
And
isomorphic. Just so roughly speaking, QA. I don't remember. Sorry, I don't remember precise shift, but well, um, yeah. So roughly speaking, QA will be ZB2 plus certain shift and shift something like one. Well, it's something like that. Sorry, I, I don't. Sorry. Well, there will be some one shift by one half, but which depends on a. So here there is certain vector right now, LA. So
all
certain
right.
phi.
So I will very roughly think that I factorize the Chow group by the kernel of the numerical equivalence map. So anyway, we
Yeah,
can get, let's assume it, maybe it's not important that
yeah. It's
gamma
not
is an
important.
element of some integer
Yeah,
lattice.
yeah. The lattice is isomorphic. The full lattice is isomorphic, of course. Z
I mean,
to
it's all important because if
plus
your
two.
Calabi-Yau is non-compact, I have no idea what you're talking about. Yeah, you
Well,
see.
first I will consider compact. So let's
All
restrict to the
right.
compact
Okay.
case,
Then
and
there is
then we have
a
a charge
Poincare
lattice.
duality. Good.
Yeah.
All right. So then your lattice is endowed with symplectic, with skew-symmetric integer form. All right.
Yeah, there is a gamma prime, so I denote it like this. Yeah, it's this symplectic antisymmetric form, which you just mentioned. And our omegas, well, in fact, we will work mostly not with omegas, but with the rational versions, which I'll denote by omega bar, and which is defined like sum over divisors of my charge, 1 over d squared, omega gamma of t. So this is definition of rational invariant. In fact, as I understand in mathematics, you first start from defining this object, and then it's a conjecture for you that this guy is integer.
It's no longer conjecture in some cases, but as for compact, I mean, integrality was proven in a very, very big generality
Okay.
for us
Then,
and for us with Maxim than other people. And
then
yeah,
even better. Because in physics, we start from integers. They are kind of integers by definition because they count
what's
some
called
number of states. And
Gopakumar-Vafa, whatever, BPS invariants. Yeah,
no,
they
no,
are
no, no.
integer.
Yeah, but these are not Gopakumar-Vafa invariants. These are
Maybe
GT.
they are. Well, anyway.
I will talk about relation to Gopakumar-Vafa later. Okay. Yeah, and let me also maybe mention just that from the physics point of view, this P0, PA, QA, Q0, they correspond to the so-called de-Brane charges. And so if we are in, so if we consider type 2A string theory on our Calabi-Yau, so then these charges precisely correspond to D6, D4, D2, D0 brane charges. So roughly speaking, they give the number of these branes. And D6 brane charge, which I call P0, it is what is also called the rank of the T invariant. So this is a rank. And okay, and now let me very briefly mention few properties of these guys. So the most important property is that they experience wall crossing. So what it means? It means that actually these guys, they are not just functions of my charge gamma, but they also depend on the moduli, which I will call ZA. And so there is a moduli space. And this moduli space is divided into some chambers like this. And my omega of gamma takes different values in different chambers. So it's actually only piecewise, not a constant function, it's a piecewise constant function. And well, in physics, we are typical, yeah, and what's the reason for that? It's because omega counts semi-stable objects. So there is certain stability condition in the game. And stability condition, it depends on the moduli, and it's expressed, well, it's captured by the so-called function, which is called central charge. It's a function which is linear in charges. Well, it can be written, roughly like Z lambda Q lambda minus F lambda P lambda, where lambda runs over 0 and A index. And typically, we're interested in the central charge function, which on the so-called which is a function of Kähler moduli of the Calabi-Yau, ZA. So in that case, Z lambda is equal to 1 and ZA, and F lambda is a derivative of the holomorphic prepotential which characterizes the modular space of complexified Keller structures of the Calabi-Yau. This is a function which is a holomorphic function homogeneous of degree 2, and f lambdas are then just derivatives of this function evaluated at these values of the parameters.
So it's a function on what?
It's a function on the Keller modular space of the Calabi-Yau, complexified Keller modular
So
space.
it's a function on the space of Keller structures, yeah?
Yes.
Very good, but do you understand that it's a non-linear space or what? Or linear? You speak about homogeneity.
Well, just this f function should be homogeneous of degree 2 because you see it depends on an additional parameter.
Because you explain why it's homogeneous, you should explain why it can be homogeneous. Can you speak about homogeneous function in the sphere? I'm in doubt.
No, wait, no, it's like, no, it's not, because this function depends on one more parameter. So this function.
There should be a fine structure or
Yeah,
whatever.
sure.
What
Yeah,
sure?
because
It's not clear because I don't know what you are
no,
talking
because
about.
yeah, I was a bit slow. So the idea is that this f depends on x0 and the xa, which I collectively denoted by x lambda, and then
What is x0 and xa?
yeah, these are homogeneous coordinates, whereas my Keller parameters.
On what space?
Wait. So
Before
I
talking
have
about coordinates, you should say what manifold you
yeah.
consider.
So I start from the Keller structure modular space, which is parameterized by ZA, and then I kind of enlarge it. I introduced homogeneous coordinates.
What do you mean parameterized? I mean, probably we will not go. Yeah, I'm afraid I will spoil your
It's all
talk.
not needed for my talk. Yeah, I'm
If
sorry.
it's not needed for your talk, then don't say it because what you are saying is technically wrong, and I don't care about type 2 string theory because I do not understand what is it, but I understand what's a Keller manifold, what's I don't know, like homomorphism. I understand mathematics, and probably people in the audience, they are not physicists. They also care more about mathematics. So just if you
Well,
don't need it, then don't speak about it.
yeah. So the only comment which I wanted to do is that in physics, we're typically interested in the central charge, which is a function of these Keller parameters. And in this case, f lambdas are also functions of these scalar parameters. But in mathematics, mathematicians consider a larger space, the so-called space of Bridgeland stability conditions.
Which nobody knows how to do it in a three-dimensional compact case. And I'm afraid that there might be, you will be in trouble when you try to
Uh,
speak mathematically. Because
well,
okay, maybe let me comment for mathematicians. So you have a derived category of coherent sheaves on the compact Calabi-Yau threefold. All right, it has K-theory, and there is a homomorphism, this Chern-class homomorphism from the K-theory to rational cohomology. Let's forget about integrality, but in fact, there is some integer structure, so to each element of the K-theory, to each class of, well, let's talk about sheaves or complexes. You can associate an element of the lattice. This lattice carries integer bilinear form. So central charge is a homomorphism from this lattice to complex numbers. All right, so I'm not even sure that you can write down the formula for the central charge. Now, stability condition, like Bridgeland, it's defined on the derived category. Coherent sheaves, which seems to be a natural T structure, for what Sergey is talking about. It's a wrong T-structure. I believe that you should look for a T-structure which consists of perverse coherent shifts. And then there is a central charge which can be written explicitly. Now, the space of stability structures, Bridgeland, not this scalar, which is a set of fixed points of certain involution on the space of all Bridgeland stability. Okay, to each point you can assign the dt invariant. It's omega, which depends. It's a function on the lattice. And it depends on the point. When you move a point in the space of Bridgeland stability structure, then you cross walls, and those walls are where the central charge maps two non-collinear elements gamma to the same array. All right, these are walls, and when you cross the walls, then there are wall crossing formulas which we developed with Maxim long ago in a much bigger generality. All right, so this is a mathematical story. The only difference is that Sergey is interested in the subspace, in the space of all Bridgeland stability structures, which correspond to the choice of Keller structure, or if you like, symplectic structure on your Calabi-Yau. So then this is a subspace, and then you have walls on this subspace. And this subspace is a base of integrable system, which is in the case of compact Calabi-Yau threefold, it's non-polarized. It's integrable system, I believe, constructed mathematically by Donaghy and Markman in the 90s. And so when you have, it's a complex integrable system, and locally, when you have a complex integrable system, there is a function called prepotential, and this is what this f of x, I believe, what he considers. So most of what he is talking about was already absorbed mathematically and generalized. So then there is a literature, and you can find precise definition. Same as for Donaldson-Thomas invariants. Thank you.
The only thing which I wanted to say here about this is that, whereas in physics we're usually interested in these particular, stability conditions, where the central charge is a function on the Keller modular space, mathematicians consider this large Bridgeland stability space.
No, mathematicians considered both. You underestimate mathematicians, because it's your space is a base of integrable system. In the case of local Calabi-Yaus, it's exactly the base of Hitchin integrable
but
system.
my point is that physicists kind of so far didn't go beyond, mostly at least, go beyond this subspace corresponding to this Keller modular space, but you did, and when you do this, then f lambdas are not anymore functions of ZA, but they are free parameters. So that's the only comment which I wanted to say. And then, as you mentioned, there are wall crossing formulas which allow to go from one chamber to another. So at least in principle, if you compute BPS indices or these DT invariants in one chamber, then at least in principle, you should be able to go to other chambers. And the chamber which I will be interested in corresponds to the so-called, at least in physics, it's called large volume attractor chamber. So it corresponds to this subspace described by Keller moduli, and then this Keller moduli, they are fixed to be the following. So the following formula, I lambda PA, and you take lambda goes to infinity, so that's the large volume limit. And here kappa AB is the inverse of a quadratic form, which will play a very important role in our story, and which is defined like this. So, and then, well, I think mathematically, these stability conditions correspond to Geiseker's stability condition.
I'm a bit confused. So you consider some subspace in the space of Keller structures, is it correct? Or you consider a path in when lambda
Yeah, I
goes
could
to.
say kind of a limiting point, but which is at a boundary at infinity, the large volume. And but since we're interested not in the point, we can talk about chamber, right? So because DT invariance.
Chamber, I thought that it's kind of a domain open.
Yeah. Yes. Well, this is I mean, so we are interested in the chamber around that point, if you wish.
Okay. All right. Okay.
Okay, and the last thing which I wanted to mention is that, there is two things. So first of all, another property which is important is that this DT invariants, they invariant, well, in physics we call about spectral flow, symmetry, but in mathematics this is, I guess, tensoring with a line bundle. So you change your Chern vector to exponential epsilon a omega a, where epsilon a are integer parameters, to this. So in the claim, if you change your Chern vector like this, then the DT invariant doesn't change. In particular, this is why, for example, if we consider rank 1 case or rank -1, so then our DT invariant, it's actually, it depends only on, not on, well, in general, depends on these four charges, P0, PA, QA, Q0, but, well, P0 is fixed. And it turns out that spectral flow invariance allows also to remove dependence on PA. So in the end, my DT invariant, it depends only on, well, on certain
All right. So let me ask you, when you call them invariants, in what sense you are as a physicist understand that they are invariants? They do
well,
not
because
change under what?
and the change of complex structure and the other
Or,
parameters like, I don't know,
or
string coupling and yeah.
they probably then they should not change when you tensor with a line bundle. Yeah.
Exactly, they do not change, and that's what
Yeah.
I'm talking. What
Yeah.
I'm telling.
Yeah. Okay. So then it's not surprising from this.
Yeah, sure. And will be interested in the rank 0 case. This is our main object of interest. And so here P0 is equal to 0. And here you can think that you can remove the dependence on QA using this invariance.
Yeah, let me ask you a question, because you see a lot of indices, sometimes it's a bit misleading. So you have kind of four components. When you
Mhm.
have, say, coherent sheaf, so you have indeed Chern classes, and rank 0 means that you consider coherent sheaves which what? Which has support on curves, surfaces, and
Or
points.
divisors on divisors of the Calabi-Yau. So four-sided.
Divisors, which mean
Yeah.
that vector bundles are ruled out, or what? Or the other way around. You allow vector bundles with support the full Calabi-Yau, or you prohibit torsion sheaves. What does it mean?
I'm not sure I understand this language. Sorry.
Yeah, but you
Yeah.
cannot speak your
Yeah.
language in mathematical audience,
Um,
ignoring that people, because this D0, D2, D4, it means nothing. You have a
uh,
coherent sheaf, it has support, yeah.
yeah, on the
And this
divisor.
support can belong to some whatever. For example, it can be concentrated, it can be a coherent sheaf concentrated on a curve. In your terminology, it's D2 brane.
Yes.
Okay. If its support is complex two-dimensional, like a surface, is it D4 brane?
Yeah, complex two-dimensional means four real dimensions. It's like four cycle is
No, no,
it's
no, no,
yeah,
no.
it's no.
D4, no, D4. So your Calabi-Yau is six-dimensional, yeah,
Yes. Yeah.
real. But I'm talking
Yes.
about complex dimensions. It's easier for me.
Mhm.
So because support of a complex coherent sheaf, it's a complex analytic subset. It is of even dimension automatically. Then the curve is D2 for you. Yeah, complex one dimension,
Yes.
it's complex surface is D4. Now,
Yes.
if it's a vector bundle, which means that supported the whole Calabi-Yau, it's D6.
Yeah, I think so. Yes.
And D6 is where? It's where you put 0 or where you put Q0.
D6 is the first component.
The first. So,
Yes.
all right. So then indeed support of your sheaf is you do not allow vector bundles
Yeah.
in your
Yeah.
story. All right.
Okay.
Good.
And then what I wanted to tell is that this invariance due to tensoring of the line bundle, it allows to not completely remove the dependence on this third component QA, but something will remain. Namely, you can decompose this component like this, where epsilons are precisely integer parameters which appear in this transformation here. But then there is some rational shift. You remember I mentioned that my charges are rational, but it's fixed in terms of my this charge, T4 brane charge. But then there is this residue class, which lives in this factor lattice. So this what remains after applying spectral flow invariance. So spectral flow allows to remove this piece, roughly speaking. And then what happens is that my DT invariant, it depends on D4 brane charge P, on residue class mu, and then on certain invariant combination Q0 hat, which remains invariant under this transformation, tensoring with the line bundle.
So
And
do you allow torsion shifts or not? Because torsion shifts they have zero-dimensional support. It's D0 brains.
yeah, so I think they're captured.
You do, but can they
Yeah,
be spread all over your Calabi-Yau threefold, or they have to belong to the four-dimensional support?
I think they have to belong to this.
What about curves?
They
Which is
also should belong
all
to the
right.
sub.
So it's some severe restriction because in general they don't have to.
Um,
It's some
well,
restriction.
maybe I'm mistaken, but I thought that they should belong. But I'm not
Strange.
100% sure.
Okay.
But okay. So so the main message is that well, there is you see that now DT invariant depends on this Q0 hat, then P is fixed, PA, and then there is this residue class, which takes finite number of values given by the determinant of this quadratic form.
What is het? Het is a combination of all.
Yeah,
Okay,
yes.
good. Mhm.
And there is a mathematical fact that this Q0 hat is bounded from above. This is the so-called Bogomolov bound.
First, not Bogomolov, but Bogomolny, probably.
Uh, I'm not sure.
Maybe Bogomolov.
No.
Actually, both. Mathematically, it's Bogomolov.
Mhm.
Yeah, it's very, very nice. Yeah.
And this
Say it again. What's the fact
that
that
if you spoil this bound, the DT invariant is zero.
how
And
Bogomolov can know this?
uh,
No, I don't know this fact. There is indeed some inequality, but how do you know that there are no semi-stable? I have no idea. So I don't know. If you find a reference for the next time.
Okay, I'll
because
try.
it's very strange. You do not have precise definition. You cannot even describe stability. Your whatever your parameters, they are fairly arbitrary, although close to some mysterious cusp point in the modular space, and so maybe I'm not an algebraic geometer to that
I thought
extent.
it's a well-established fact, but
Maybe it's well established, but you should formulate it in the language that we understand, maybe. Because basically what you're telling me that if you take a Keller structure which is close to some particular limiting point, which actually limiting point does not belong to the modular space of Keller, it's kind of so your Keller structure is on a certain path which goes to certain limit, and when you compute the number, say, call it number of semi-stable coherent sheaves, or maybe perverse coherent sheaves with this Keller structure, then the certain inequality has to be satisfied. Let me think for a second. Yeah, I think I understand what do you mean, but I'm not sure I know this mathematical fact. Basically, it's an estimate from below, I believe, on the value of the central charge of your object. You say that the absolute value of the
I'm
central
not sure.
charge is bounded from below, but the norm of
No, I'm not sure.
of the norm of the cohomology. Because otherwise, I don't know what you're talking about, frankly.
Well, I can try to find the reference for
All
next
right.
time.
Mm-hmm.
And due to this fact, we can define the generating function of this rank zero or rank zero DT invariants like this. So we sum over Q0 hat, since the sum is bounded from above, so the sum is well infinite only in one dimension, in one direction. And then the claim that if you sum not the integer DT invariants but the rational version, so this generating function, which you see is a vector valued object because it depends on mu, which takes finite number of values. So the claim is that this vector valued object has very beautiful modular properties. So that's the claim. And next, I will.
Maybe it does, but I do not understand. So your tau appear, your Q0 hat is
It's
an
conjugated
element
to tau.
is an element of a lattice. Yeah, it's an
Yeah.
element of the lattice. And what do you mean that you take exponent of the element of the lattice?
Well, Q0 is Q0 hat is just like an integers plus certain shift. I don't know, call it delta, delta some rational number.
It's a number.
Yeah.
Sorry.
Yeah, it's a number. Yeah.
Yeah. Okay. Good. Yeah.
So, and
And
next I was supposed to explain you the origin of these model properties and explain how they look like, these model properties. So can I explain at least where
yeah.
they come from?
You can take maybe 5 more minutes. Yeah.
Okay, so where they come from? Here, sorry, I have to go a bit to physics because otherwise I don't have pure mathematical explanation. But it will be not so difficult. Let's start from now. Before I was talking about type 2A, now I want to talk about type 2B on a Calabi-Yau. And type 2B on a Calabi-Yau corresponds to certain effective theory in 4 dimensions, which is called n equal to supergravity. And there is a fact, a very simple fact, that if you take the low energy limit of this theory, its action is completely fixed just by 2 modular spaces. So there are the so-called there are certain two manifolds, which are called vector multiplet modular space and hypermultiplet modular space. So the whole modular space is just their direct product. And if you know the metrics on these modular spaces, you know completely the theory. That's the claim. Now, what are these modular spaces? This one is very simple. It's just the space of complex structures of the Calabi-Yau. So it's a special Kähler manifold, and we know everything about it. Well, at least we can say so. And but this object is more complicated. There are two reasons why it's more complicated. First of all, it's a quaternion Kähler manifold. So already much more complicated type of geometry. And second, the metric on this manifold gets, well, from the physics point of view, quantum corrections. Quantum corrections. And among these corrections, there are the so-called d-instantons. And so how these d-instantons look like? Well, roughly speaking, they are just exponential corrections, exponential terms in the metric, which is kind of the exponential of the volume of the corresponding cycle. Let's call it. And the cycle is characterized by the charge gamma, and there is some string coupling. But what is important for us is that in front, there is dt invariant, which depends on the charge gamma. So all these corrections, they depend on these dt invariants. Therefore, dt invariants, they affect the metric. That's the message. And among these, d-instantons, there are the so-called d3 instantons. So they correspond to d3 brains, d3 brain wrapping some divisor, yeah, on the Calabi-Yau. So d3 brain is an object which has
I am confused because you kind of change the terminology. So far in what you spoke before, you kind of get rid of time. So your D2 corresponds to complex one-dimensional, D4 corresponds. No, when you speak about D3, you are talking about some physical string theory. So time is involved. Is it correct? Because there are no 3 is an odd number. It cannot you cannot have 3 1/2 3 divided by 2 support of a coherent sheaf.
Yeah. So the point is that D3 brane has 4-dimensional walled volume.
No. And when you speak about 2B, I am totally, you see, it's terminology which tells me nothing. But where you have type 2, type A, you have even dimensional branes. So, and so far we spoke about type 2, whatever, yeah. So then we have coherent sheaves. So type B, probably it's D3, it's a Lagrangian, it's a dimension.
No.
Then I do not understand what you're talking about.
Wait a second. I'll explain. So before we talked about type 2A and we talked about BPS states in that theory. So from the physics point of view, these DT invariants, they count BPS states. What are BPS states? These are states which look like a particle. So it means, for example, you take D4 brane. D4 brane has 5-dimensional walled volume. You wrap it on a divisor which has 4 dimensions. So you still have 1 dimension, right? Which corresponds to time. You mentioned time, right? So precisely we will have a point-like object which moves in time. So this is the remaining 1 dimension. Now we go to type 2B, but we consider type 2B on the same Calabi-Yau. And in this type 2B, we consider instead of D4 branes, we consider D3 branes, which have 4-dimensional walled volume. And we wrap all these 4 dimensions on the same divisor, so that from no dimensions remain. It means that from the point of view of these 4 uncompactified dimensions, it's a point-like object. It doesn't move in time. This object lives in Euclidean theory, and this is why it's an instanton. So these instantons, they are objects in Euclidean theory.
Which means that I cannot see it mathematically because string theory does not exist mathematically. And what we spoke before and what I understood, it's an interpretation of BPS, BPS invariance in terms of something which mathematically meaningful, like number of semi-stable coherent shifts, blah, blah, blah. Now, what you are talking now about, it lives in the Euclidean space, which is sort of transversal to our Calabi-Yau. So it does not kind of...
No. The object lives on the same Calabi-Yau, and it does not have any dimensions in the transverse directions.
There are no transverse direction in mathematics. Yeah, R4 does not exist. There exists only Calabi-Yau. So if it lives on Calabi-Yau, then tell me what is it? Before it was coherent shift. Huh?
Exactly the same coherent shift, nothing more. Exactly the same object.
So I do not understand. So far, your coherent shift could have dimensional support like on curves, surfaces, or whatever. This D3 is, if it's a coherent shift, then what's the dimension of his support?
Divisor, the same divisor which we had before.
So then D3 is just a notation from, it does not make any different mathematical...
Yes, from the mathematics point of view, it's the same object which we had before. Just from physics point of view, we live in a different theory. That's it. Yeah. Well, and the claim is that these objects, they generate exponential corrections to the metric on this manifold. And the claim, so I claim that in physics, we know how to compute these corrections explicitly. So I know that all corrections to all orders, if so in general, there are infinitely many orders in the expansion in these exponentials, and I know all these orders, how they correct the metric here. That's one statement. The second statement is that this theory is known to be invariant under S-duality.
And, I don't know what S-duality is. Sorry.
It's just
I pretend that I don't know.
Okay, I will tell you now. So what it means is that there is certain SL to Z group, symmetry group. Now,
symmetry group of what? Of physical theory?
Yeah, it's a symmetry group of physical theory. But now let's forget about this string theory, which it's difficult for us, right?
At least for me.
But this theory is concrete, very concrete field theory. So the question, how is this SL to Z reflected here? The answer, very simple. This SL to Z must be isometry of the metric on this modular space. It must be isometry of this modular space.
Which modular space? Of the MH or the...
MH. Yeah, which is quaternion-Keller. So in other words, this metric, which gets these instanton corrections, must carry an isometric action of SL to Z. And of course, this cannot be true for any values of DT invariants. This will impose certain restrictions on them. And my claim is that the restriction, this restriction can be derived, and it's precisely the restriction on the generating functions, which I defined on the previous slide. And the restriction is very simple. Well, not very simple, but let me formulate at least in words. So let's assume that our divisor, which I call dp, that it's can be decomposed into...
what is dp? You say our divisor. What divisor?
It's divisor up by, characterized by the charge PA.
All right, support of coherent shift. All right.
So let's assume that it's decomposable into R irreducible divisors. Okay? Then, if R is equal to 1, the corresponding generating function must be modular form of weight B2 minus B2 by 2 minus 1.
Why?
This can be derived, as I explained to you, according to this logic, from the requirement that MH carries a symmetric action of SL to Z. If R is larger than 1, then again, HP mu is vector valued mock, or more precisely, okay, mock modular form of depth R minus 1. And we know the precise modular anomaly equation which it should satisfy. And this modular anomaly equation I just wrote on the next slide. Namely, where that this modular anomaly expression is, modular anomaly equation is expressed as an equation for the modular completion. So this is a modular completion, which means that, so what this equation tells you is that this particular combination of generating functions must transform as the standard modular form. So it's a modular form of the same weight which we had before. So that's the claim, the big claim, the main message. So the physics allows to you to derive the modular properties, and the modular properties are encoded in this expression for the modular completion.
So you cannot spell it out in physics without talking about this mysterious and unknown metric.
Indeed, the metric, the complete metric is mysterious and unknown, but we do know all these d-instanton corrections to it. There is some part which I don't want to mention, which we don't know, but this part we know, and it passed many, many tests.
Yeah, you see, Sergey, I mean, I would be at least to learn something from your today's talk. I would like to understand what is d-instanton mathematically. Because for me, instantons, I mean, is it something which lives on the brain? I mean, it's some, because when you say coherent shift, so why do you call it instanton? I somehow lost in terminology.
Yeah, for you, I think, well, if you more or less understand what these BPS states are,
yeah, this I understand.
Then instantons for you would be if you forget about these transverse directions, because you told me that they don't exist for you, then for you this is the same, absolutely the same object. The difference precisely happens in these remaining transverse directions. Because BPS states they correspond to particles, and instantons, they are like, so particles are like like one-dimensional objects, like they have one-dimensional world line, and instantons, they're zero-dimensional objects. But these dimensions, they happen in the transverse directions. If
yeah,
they
but
don't exist,
what I do not understand that previously when you say that we have, I don't know, like D2 brain, something which corresponds to a coherent shift supported on the curve. You did have the transversal time direction, yeah?
Yes.
So then the honest object, in fact, it lives in the real, whatever, 2 plus 1 direction, yeah?
Yeah, there is R3 plus 1.
But this its behavior in this time direction was irrelevant for us because I can count them forgetting now. In the case of instantons, from physics perspective, it's also an object which lives in dimension 4 plus 0, yeah? So like there is no time, or at least, yeah. But its behavior, whatever, as a mathematical object, I mean, how to count these d-instantons? for example, if I want to ask a question how to count these d instantons, what should I do mathematically for that?
Well, the claim is that their number is the same as the number of BPS states in the dual theory. They're the same, the same BPS states. There is no difference.
But they but they correct in some non-trivial way, which you wrote. They correct the metric. Okay.
Yeah, and precisely because only instantons which have zero dimensions in these transverse directions, they can correct the metric. This is a feature of instantons.
Yeah, all right. So then I recall that we had with Maxim some mathematical model for this quantum Keller, for this quaternion Keller manifold, but frankly speaking, I forgot because it was kind of decades, maybe long ago.
There is an open problem about this space is that we don't quite understand how to, because there are additional type of corrections which come from NS5 brains, and these objects we don't know how to include at multi-instanton level. Well,
all right,
this is
all right. Probably, I think we should finish today, and so you will have one more. Like the most interesting part you left for the end of your lectures. Yeah.
Yeah, because it goes like 2 times or 3 times slower than I expected. But tell me what you because what you want to listen in the sense that there are two kind of, well, maybe three things which I can tell you. It will be impossible to tell them all. This is what I wanted. But so the one thing is to explain how this modular anomaly looks like in more detail, like what are these coefficients are, and what is it?
Okay, first,
The,
second.
the second is how to solve this modular anomaly equation, how it can be solved. And so this is the second step, and this step, when you solve this modular anomaly equation, you still get certain ambiguity in the solution. So the third step is how to fix this ambiguity, in particular for the case of compact Calabi-Yaus.
But it does not look at three different subjects. They linearly ordered. So
Exactly, but
your main thing is this modular anomaly equation. And suppose that you can solve it completely, like you know all the coefficients. What does it tell us about DT invariants?
as I told,
Why
so
we should be happy as mathematicians? Yeah.
well, again, you can solve it up to certain ambiguity. So if you somehow are able to fix this ambiguity, and in some cases we can fix it, so
Yeah.
then you get explicit expressions for the generating functions, which means that you get access to this rank 0 DT invariance. And it turns out that also sometimes this allows you to compute also, for example, Gromov-Witten invariance to in the cases where you couldn't do it before, for example, to the genus which was inaccessible before.
Well, if you can, I mean, for the sake of the audience, I believe mathematical people are interested in Gromov-Witten invariants, maybe DT invariants. It would be nice if you can explain this part. Suppose that you can solve these equations. What the consequences for the enumerative invariants? And because when you, even if you explain how you ingeniously fix the ambiguity and whatever makes it finite dimensional, then fix, it's nice, but what we can learn from this. So it's kind of, so I don't know. I mean, so since it's not a half a year course, so you have only limited time. So you should explain the ideas, and then if time permits, some technical details. Because if you explain technical details and people will not know why they should learn it, so it will be forgotten.
Okay,
So
then I will not explain what are these coefficients, and yeah. Okay, so I'll try to concentrate on ideas and
yeah,
yeah.
all right. Okay, so I believe we are very much over the time. So let's leave the questions until Sergey's last lecture tomorrow. Okay, thank you. And this is it for today.